Okay. Good morning, gang. Looks like so far just two folks here. Um, I imagine the rest will start trickling in a few minutes. I don't know about you guys. It's a rainy, kind of dark morning here in Gainesville, so I had a difficult time getting up today. I imagine there are others in the same situation. But we do have quite a lot to do. As discussed, as discussed last time, this week's task is to continue where we left off last time in 11.9 by beginning to talk about calculus operations on power series. So all of last week was about introducing power series. We learned that geometric series trick for finding power series representations of simple functions, i.e. rational functions. But this week we're going to go further. We're going to start learning how to find power series representations for all sorts of new things. We're going to cover two sections. Oh, I always forget this pen hates me. Today the 9th. All right, so today we're going to cover the rest of section 11.9, and we're going to introduce section 11.10 if there is time. I wonder if this guy works. Good morning, Hatanji. If you'd like to see those problems, yeah, we can take a look at those. I guess I should tell you guys too, your tests are graded. You probably all noticed, but I finished grading your tests yesterday. The scores are up. Unless for some reason you didn't submit the work in Canvas. If you submitted the work elsewhere and were not able to get the work to submit through Canvas, I'm going to grade those when I grade the makeup tests. But if you took the test normally, like with the rest of the class, or even if you took it at a strange time or a different place, as long as you got the work submitted on Canvas, your grade should be in. The grades were not awesome, but this is a hard test. There were good grades. There was one, I don't know if it was in your section. I think it was. There was one nearly perfect score, but the grades varied quite a bit, which is to be expected for this material. I did do my best to warn you that this stuff is hard. And that really required a lot of prep. If you're not happy with the grade on the test, then I strongly encourage you to send me an email. If you're worried about your grade in the class, send me an email. We should be talking about these things. You shouldn't be worrying about them on your own. Zach asked a good question. One of the study guide grades coming as soon as I can. I've got two other sections that had tests. I need to get those knocked out by Wednesday. And so I'll probably not be able to loop back and do your study guides until Wednesday. That's a guess. If I happen to find more time tomorrow than I'm expecting to, then I may be able to get them done Tuesday. But I would say probably after Wednesday. Let me take a look at the homework due dates here. So I think the reason I split 11.9 into two pieces was because you didn't have a full week, right? That's why we're breaking section 11.9 into two different pieces, because you only started homework 10, or we only officially had the lecture for homework 10 last Wednesday and last Thursday. So rather than giving you a full week's worth of homework, I chopped half of the second section off, and that's what we're going to begin right now. But as always, if you need more time on that homework, you can submit an extension request, and I will happily grant it. No questions asked. Okay. Other questions along these lines? Yeah, let's do it like this. Okay. So because Tanji asked for them, Antoine asked for them, we're going to take a look at numbers 21 and 22 from homework 10 before we get started with the new material. I think that's fine. Okay, yeah, these are both great problems. I think it may be a little bit redundant to do both of them, however. So I will do number 21. All right, so I think, Hutanji, once I show you how to do number 21, you won't have a hard time with number 22. So try to pay careful attention here and then apply the same tricks to number 22. It'll work out nicely. You may have a different randomly generated number here than I do, but I have 81 and it will always be a perfect square. Okay, so they give us a function and we want to find a power series for it. And remember, the only thing that we know is the geometric series trick. That's all we got for finding power series. So we're definitely going to need to use that geometric series trick. I would begin by bringing the x squared off the top out front like this, and swapping the 81 and the x to 4 like this. Does everybody agree that algebraically these are the same? This is the same as the original function. Remember what our goal here is. We want to get this in the form 1 over 1 minus r. So we can use that geometric series trick. So my next step would be to force factor an 81. And now this 81 can come out similar manner to the x squared. So this is x squared over 81 times 1 over 1 plus x to the 4 over 81. And this is looking much closer to my 1 over 1 minus r thing. So my last little step here would be to think of this, instead of being 1 plus that, being 1 minus the negative of that. So my last little bit of algebra here looks like this. And now this piece I can write as a geometric series, and then I can multiply these things back in. So that's the big step. That's where we introduce the series. This, of course, is still being multiplied. And now I can start cleaning it up. The negative here inside the whole power is the same as having a negative 1 to the n. I've got an 81 downstairs, so that's over 81 to the n. And then I've got x to the 4 all to the n. That's x to the 4n. And now finally I can bring these guys inside. I'll still have my -1 to the n. Downstairs here I have 81 to the n times 81. That's 81 to the n plus 1. And x to the 4n times x squared is x to the 4n plus 2. And that's job done. And I know you said you wanted to see 21 and 22, but 22 is very, very similar to this. All the same tricks. The main trick for all of the homework problems in homework 10, remember, is the geometric series trick. You're always trying to use this. Now this week we're going to go beyond that. Actually, today we're going to go beyond that. But we'll still be using that as our jumping off point today. Any questions on this problem? All right. So that's a nice sort of recap, get us back on our feet from where we were last week, reminding us what we were doing. Today I want to talk to you about integration and differentiation of power series. We mildly introduced this last week, but it's a big, big deal. It's a big enough of a deal that I think you could probably make it its own section in the book. But it's folded into section 11.9 here. That's okay too. Remember, a general power series could be centered anywhere. So it looks like Cn times x minus a to the n. A neat fact, this is definitely automatically differentiable. And its derivative, f primed, you can start writing down without thinking too hard about it by just differentiating this piece, right? This is the only place there are x's. So if I want to differentiate x minus some constant all to the n, that's a chain rule derivative. I use the power rule on the outside, leaving the inside alone. And then I would multiply by the derivative of the inside. Well, the derivative of x minus a is 1. The only other catch here is that the starting term, starting index, the n equals 0 term, goes away because the n equals 0 term here is constant. So this guy gets bumped up to a 1. And the rule here, people end up always asking me, do I need to bump the starting index or not? We bump n equals 0 up to n equals 1 if and only if the original series has a constant term. So like the n equals 0 term in this most general series is the constant C0. That constant differentiates to 0, it goes away. Everything else is just as you would think it is. You just differentiate the x's. Also, capital F of x is integrable. Definitely if it's differentiable, it's integrable. And the integral of f is c plus sigma n from 0 to infinity Cn times 1 over n plus 1 times x minus a to the n plus 1. Same sort of deal. I paid attention only to this piece when I integrate. If I want to integrate something like this with respect to x, that means this power is going to go up by 1, and then I'm going to divide by the new power. So the n power becomes an n plus 1 power, and I divide by the new power. You can think of it as a tiny little u sub, right? Where you u sub like z equals x minus a, then this would be z to the n. Z to the n integrates to z to the n plus 1 over n plus 1. So the formulas here are what you would think they are. There's nothing tricky except maybe this index shift, right? The fact that when you differentiate, sometimes the starting term goes away. But the rule you have to remember for that is here. And this stuff is not very hard to keep clear in your head if you practice it. I know that I sound like a broken record saying, practice, practice, practice. But if you practice this shit, it will stay clear in your head. If you do enough of these problems in good faith, you will not have a hard time remembering this. The proofs of this theorem are trivial. You just write out the terms of the series and you integrate them and differentiate them. I wouldn't tell you that they're trivial and then not show you anything. So let's take a quick look. F of x is c0 plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a cubed, and so on. Showing that this function is differentiable, that's actually hard. Showing that you're allowed to take the derivative, that's a little bit more challenging. Frankly, it's a little bit beyond the scope of this class. But if you trust me that you can differentiate this thing, and you should, because you've seen examples of functions that these can represent, and they're all differentiable, then you just dive in here taking the derivative. So if you take the derivative here, c0 differentiates to 0, it's a constant, plus c1 times x minus a. If you differentiate that, you just get c1 plus c2 times x minus a squared. If you differentiate that, you get c2 times 2 times x minus a to the 1. c3 x minus a cubed, if you differentiate that, you get c3 times 3 times x minus a squared, and so on. So you see that the n equals 0 term is gone. All right, the n equals 0 term dies. So what you're left with is going to be a sum from 1 to infinity. The first term that you have here is the c1 term. And what pattern do these all follow? Well, the power came down n was reduced by 1. It's just like it is when you differentiate a polynomial. And the reason being is that these really are just infinite polynomials. So that's the proof for the derivative. We just rewrite this sum back in sigma notation. And the integral of f of x same shit. I'm doing an indefinite integral, so I'm going to get a plus c. And then imagine doing a little u sub here. Imagine you u subbed for x minus a. So here I would need to integrate. We're going to make the u sub equals x minus a. Du is just dx. I'll go ahead and use the letter u. Then this will be the integral of c0 plus c1u plus c2u squared plus c3u cubed, and so on. Done du, which is equal to c plus, now if I integrate c0 du, I'll get c0u. If I integrate c1u du, I'll get c1 times u squared over 2. If I integrate c2u squared, I'll get c2 u cubed over 3. If I integrate c3u cubed, I'll get c3 u to the 4 over 4, and so on. And then plugging back in for x minus a's, this is constant capital C plus c0 times x minus a plus c1 times 1/2 times x minus a squared plus c2 times 1/3 times x minus a cubed plus c3 times 1/4 times x minus a to the 4. And if you take this and rewrite it in sigma notation, you get c plus sigma n from 0 to infinity cn times 1 over n plus 1 times x minus a to the n plus 1, right? c0, so here n is 0, would be c0 times 1 over 0 plus 1, that's 1 times x minus a to the 1. Okay, that's this. c1, so n is 1, you would get c1 times 1 over 1 plus 1 is 1/2 times x minus a to the 1 plus 1. So this really is it. And that's the proof. Okay. So this is how we integrate and differentiate power series. You integrate them and differentiate them the same you would if they were polynomials. You integrate them and differentiate them one term at a time. We call this term by term. All right. Questions on this? Just on the theorem or the proof? As always, the part you're responsible for is the theorem and being able to use it. I'll say one more time, this is the piece that people have trouble with. When you differentiate a series, what do you do with that starting index? Do you bump it up from n equals 0 to n equals 1 or no? Do you bump it up from n equals 1 to n equals 2 or no? The rule is you bump the starting index up by 1 if the original series has a constant term. and only if the original series has a constant term. So in other words, before you differentiate a power series, you should write out the first few terms to see if there is a constant term. All right, I'm gonna show you some cool shit now. You ready for cool shit? This first one won't be super exciting, but it is important. Indeed. All right. So this is an example. Sorry. Can we find a power series for 1 over quantity 1 minus x squared? The issues people have with these sort of problems, this requires differentiation. I'm going to say it at the outset, is figuring out which direction to go on the calculus ladder. This will require differentiating a power series. So I'm going to recognize this as the derivative of something. And then I'm going to find a power series for the something and then differentiate it. When I see 1 over 1 minus x squared, I think this is probably the derivative of 1 over 1 minus x. Because of how power rule derivatives work, right? 1 over x squared is the derivative of something like 1 over x. You combine that logic with the chain rule, and you get this guess. This guess turns out to be exactly correct. You can check it. So this is my guess. I'm going to check. The derivative of 1 over 1 minus x is the derivative of 1 minus x to the negative 1, which would be negative 1 times 1 minus x to the negative 2 times, by the chain rule, negative 1, which is indeed 1 over 1 minus x squared. What that means is that my function, the thing I want a series for, is the derivative of something I know how to find a series for. So I'm going to find the series for this, differentiate it, and that will give me the series for my function. Are we clear on that logic? Okay. So then 1 over 1 minus x squared is the derivative d dx. So my function is the derivative of this guy. This guy is easy to find a power series for. So I'm going to find a power series for this, differentiate it. That will give me the series for my function. The series for 1 over 1 minus x, that's just the straight up geometric series, sigma x to the n, summed from 0 to infinity. Before I differentiate this, I should ask, does this have a constant term? because remember, that's what tells me whether or not to bump my starting index. Well, sigma x to the n, sum from 0 to infinity, that's 1 plus x squared plus x cubed, and so on. Yes, it does have a constant term. Right, it's right there, it's the 1. So I will need to bump my starting index from n equals 0 up to n equals 1. So the derivative of this series is the series sigma n from 1 to infinity, n x to the n minus first power. That's it. So the function capital F equals 1 over 1 minus x squared. It has power series sigma n from 1 to infinity, n x to the n minus 1. All right. This is a very kind of gentle example. Not all examples will be this gentle. First thing you had to do is come up with this guess. This is the hard part. We check our guess by differentiating to verify, but some people, in order to come up with this guess, like to integrate this function. That works, but then you're going to forget, like, what's the main move here? The main move here is differentiation. I recognize that this function looks like the derivative of something else. And then I made this guess. Sometimes this guess won't be exactly correct. You'll be off by a little bit and you'll have to go back and fix it. That's why we check. And while you could make sure that you always come up with the right guess by integrating, that also has the tendency to confuse people as to what they need to do to that series to get where you need to go. So this is my suggested path. If you think that your function is the derivative of something else, go ahead and take a stab at what you think it's the derivative of. Basically, you're doing an integral in your head. Then check. If you need to correct this guess, correct it. Then go ahead and do your computation. And when you get to the place where you're differentiating a series, you always need to ask the question, does this have a constant term? The only way to answer that question clearly is to write out the first few terms of the series. So every problem where you're finding a power series by differentiating should have each of these elements. You should acknowledge that your main task here is to differentiate or integrate something. Then take a stab at what it is you're going to differentiate or integrate. Here, I took a guess that my function was the derivative of 1 over 1 minus x. I knew that a priori because I made these notes, but it was a reasonable guess and it wouldn't have been hard to come up with thinking about the power rule. Then I checked that guess. Then I went ahead and did the calculation where I say, okay, my function is indeed the derivative of 1 over 1 minus x. I'm going to write 1 over 1 minus x as a power series and then differentiate it. When I get to that step, I ask, does this have a constant term? Because I know that will affect the result of the differentiation. I write out the first few terms of the series to see if it does or does not have a constant term. In this case, it did. So when I go ahead and do my derivative, which is like easy, right? Just differentiating x to the n, that's always n x to the n minus 1. I remember to bump the index because the n equals 0 term, that constant term, this 1 is going to differentiate to 0. It's going to go away. So this term right here is the n equals 0 term. He's going to die when I differentiate. So my new series no longer has an n equals 0 term. It begins at 1. And for this problem, that was it. That was the whole game. Questions on this example? Okay. Cooler examples. I did the arctangent function for you guys last week, right? I think so. So instead, let me let our next kind of, while we're just meeting these things, exciting example. We defined a power series for the natural log of 1 plus x. Is this the derivative of anything you know well? Is there any function you know differentiates immediately to natural log of 1 plus x? Good. Yeah, no, this doesn't look like the derivative of anything I know, but it does look like the integral of something. Ln of 1 plus x is the integral of 1 over 1 plus x. So here's my guess. And you can check it. And it works. There is a plus c involved, but we're going to shove that onto the right-hand side. All right, so this is a correct statement. Therefore, my function is the integral of 1 over 1 plus x dx is the integral of 1 over 1 minus negative x dx is the integral of sigma n from 0 to infinity negative x to the n dx is the integral of sigma n from 0 to infinity negative 1 to the n x to the n dx. And whether you're integrating or differentiating a power series, you need to write it in this standard form before you can do either. I could not take the integral at this step because I've got like negative x to the n. I don't know how to handle that inside of a series, inside of an integral. I need to write it like this. I need to write it as sigma cn times x minus a to the n. Here a is 0. We have to write it in that standard form. But once we write it in that standard form, we know how to integrate that. That's constant capital C plus sigma n from 0 to infinity. The Cn come along for the ride times. We increase this power by 1 and divide by the new power. So for some constant C, the natural log of 1 plus x is equal to this stuff, C plus sigma n from 0 to infinity I'm going to group the negative 1 to the n and the n plus 1 like that, x to the n plus 1. When you use integration to find a power series for a specific function, when the problem isn't just integrate this series, but find a series for this function, natural log of 1 plus x is just one function. So this c has to have one specific value. I got to find c, right? For some constant c. For what constant c? So now we need to determine the value of c. Okay. Any ideas how we could do that? Think back to the end of Calc 1, where you're given some problem like f prime equals some function, and then f of 0 is some number. Recover the function f of x. That's basically what you have here. You integrate on both sides, and you get f of x is equal to some constant plus your function. No. Yeah, so Hotanji asked, do we not need to bump the starting index here? Why is this n equals 0, not 1? Remember that theorem. So the only case where we ever bump the starting index is when we're differentiating. If you're differentiating and your series has a constant term, then you need to bump the starting index. But when we integrate, we never need to bump the starting index. The idea here is that when you bump this from a 0 to a 1, it's because the n equals 0 term in the original series gets differentiated away. But when you integrate, nothing ever goes away. In fact, you pick up an extra constant. So we never need to bump the starting index when you're integrating, only ever when you're differentiating. But we do need to figure out what c is. And the trick to doing that is to plug in a particular value for x, usually the center of the series. Let me write out what we have here. What are the first few terms of this series? When n is 0, you get 1 over 1 times x to the 1. When n is 1, you get negative 1 over 1/2 x squared. And it continues like that. Plug x equals 0. Then your left-hand side becomes the natural log of 1. Your right-hand side becomes c plus 0 minus 1/2 times 0 squared plus 1/3 times 0 cubed minus 1/4 times 0 to the 4 plus, and so on. This stuff is definitely all 0. And this is 0. So you get 0 equals c plus 0. It tells you that c itself needs to be 0. Thus, the natural log of 1 plus x has series expansion. This thing, right? C is just 0. This guy is a special power series that you need to remember. Right? So from last week, the only special power series that you needed to remember forever and ever was the geometric series, the 1 over 1 minus x series. This week, I'm going to give you a handful of other power series that are so important you need to remember them forever and ever, amen. Not just for this class, but for differential equations, Calc 3, Physics 1 and 2. They will be important in all of those places. This is one of those series. Along with this series, you want to remember its interval and radius of convergence. So I'll give you just the IOC because that encodes the rest. The IOC here is -1 to 1, like this. Closed on the right, open on the left. The center is 0, so the radius of convergence is 1. Gotta remember this. If you forget the IOC, that's not the end of the world because you can always cook that up using the ratio test. But you need to remember the series because there will be problems later on where this is your starting point. You don't want to have to go back through this whole procedure in order to get to the starting point. There's one other very important series that I can cook up in the same manner for you, and I think it's the case that I did this for you last week. Before I do that, that's going to be the arctan series. Any questions on what we did here? Yeah, it's a sad thing. Okay, if there aren't any other questions on this, then I am going to move on. I'm going to go back through that arctangent series for you guys because that's important. We did it kind of informally last week in a very hurried way. Similarly, we can find a series for the inverse tangent of x. Because I know, this isn't even a guess, I'm not going to bother checking it. I know that the inverse tangent of x is the integral of 1 over 1 plus x squared. Which is the integral of 1 over 1 minus negative x squared. Which is the integral of sigma n from 0 to infinity, negative x squared to the n, which is the integral of sigma n from 0 to infinity, negative 1 to the n, x to the 2n. All right, so from here, I just integrate the x to the 2n piece. Everything else is constant with respect to the integral. I get my plus c out front, sigma n from 0 to infinity. Negative 1 to the n comes along for the ride. I add 1 to the power, that's going to be 2n plus 1, so this will be x to the 2n plus 1 divided by 2n plus 1, like this. And just as in the previous guy, now we need to find c. When you get to this step, you need to write out the first few terms of the series. Do not try plugging 0 into the series as it is. So when n is 0, what do I get? I get 1 over 1 times x to the 1. When n is 1, what do I get? I get minus 1 over 3 x to the 3. And then plus 1/5 x to the 5 minus 1/7 x to the 7, and so on. And into this, I plug x equals 0. The inverse tangent of 0 is c plus 0 minus 1/3 times 0 cubed plus 1/5 times 0 to the 5 minus 1/7 times 0 to the 7, and so on. And again, this is all 0, this is 0, so you get 0 equals c plus 0, which means c has to be 0. So the inverse tangent of x has series representation sigma n from 0 to infinity, negative 1 to the n over 2n plus 1 times x to the 2n plus 1. And this is another one of those series that you need to remember. This is a starting point for a lot of other important problems. It's not just the end point for this problem, it is the starting point for many others. And you should also know the IOC. Again, the IOC you could cook up using the ratio test if you're patient. Use the ratio test, then you check your endpoints. The ROC here is definitely still 1. And then if you plug in either positive 1 or negative 1, you will get a convergent series. Which brings me to an interesting thing. So I'm going to pause here. We've seen an example of how to differentiate series and a couple of examples of how to integrate series. And what I'd like to do now is look at how the interval of convergence of the differentiated or integrated series compares to the interval of convergence of the original series. First, though, any questions on this? So let's talk about intervals of convergence for series before and after we integrate them and differentiate them. This is going to be a theorem. If f of x, capital F of x, is this power series, has radius of convergence R and interval of convergence let's see, actually there's no nice way to say this because it would have to be one of a bunch of things. Let me just talk about the radius of convergence. Then both the integral of f and f prime, both of those series have radius of convergence R also. In other words, when you integrate or differentiate a series, the radius of convergence cannot change. The original radius of convergence is the same as the radius of convergence for the integrated and differentiated series. However, the IOC for f prime of x may lose an endpoint or two. And the IOC for the integral of f may add an endpoint or two. So when you integrate or differentiate a series, you do not change the radius of convergence. The radius of convergence is not altered by either integration or differentiation. But differentiation may end up losing an endpoint, and integration may end up picking up an endpoint. My favorite example of this actually comes from what we just did. Recall. So rather than a proof here, I'm going to give you some neat examples. We get the arctan series which has IOC closed -1 to 1 by integrating the 1/1 plus x squared series which has IOC open -1 to 1. So when you integrated this series, which doesn't include either endpoints in its interval of convergence, you get this series, which includes both endpoints in its interval of convergence. The natural log series also picks up an endpoint. Not both that time, just one. So if you were to differentiate this series, you would get this series, and you would lose both of your endpoints. if you integrate this series, you get this series, and you pick up both of your endpoints. Cool stuff, right? The question, why doesn't the radius of convergence change? Has a relatively easy proof. So easy, in fact, it's relegated to the exercises of your calculus textbook. So it's kind of a bonus exercise. Prove the theorem. I.e., show that all three series below have the same radius of convergence. First series is the original. Second series would be the derivative. And the third series would be the integral. Show that all three of these series have the same radius of convergence. Hint. Show that L from the ratio test is the same for all three. It's not hard. And it really is an exercise in your textbook. I don't think it's an exercise that carries over well into WebAssign because you can't like click a button or type in an answer. But it definitely is in the physical book. If you have a copy of the physical book, section 11.9, this problem's right there. And it's a really good problem. So I would like for you guys to try this. Okay, how are we doing on time? We got about 10 more minutes. We've only done one example of differentiating a series. So let me grab one more example where we have to differentiate a power series. This is all still coming from the latter part of 11.9. What the hell? Oh, that's the end, it's not page down. Okay, page down is there. So what's a fun one? Those are all too easy. Oh yeah, let's do something like this. Let's do some shit like 15 or 16. These would be good. I'll tell you right now, I am going to assign this problem, 13 this week. This is one you're going to have to work out. You're going to first want to get a power series for this. So you're going to start with 1 over 1 plus x and then differentiate it to get a power series for this. Then you'll differentiate again to get a power series for this. And then you'll multiply by x squared to get a power series for this. But there are some things that we haven't experimented with. Yeah, right here. Problems 1 and 2 are the theorem I mentioned, right? If the radius of the original power series is 10, what's the radius of the differentiated power series? If the other power, if that power series has interval of convergence, this, what can you say about this? Same shit. All right, let's do 15 and 16. So we actually haven't done any examples like these, and these are important. So I told you that the natural log and arctan series are important, right? This is why. Let's do natural log of 3 minus x. The thing we want to remember here, you don't want to cook this up from scratch. Remember that the natural log of 1 plus x has a certain power series. It's the sum from 0 to infinity, negative 1 to the n over n plus 1 times x to the n plus 1. You're going to use this to get the series for this. You might say, how the fuck am I going to do that? These aren't the same function. Well, it's the same sort of algebra tricks that we used to make the geometric series trick go through. So the natural log of 3 minus x, first I want to make this a 1, so I'm going to force factor a 3 inside. So this will become 1 minus x over 3. Within my natural log. And now I've got this log with a product inside, so I can rewrite that as ln3 plus ln 1 minus x over 3. And now that's ln3 plus the ln of 1 minus, plus negative x over 3. So you can take this series and apply it here. The ln3 out front is going to come along for the ride. And then this piece, I know how to write as a series. It's the natural log of 1 plus something. So I take this formula, and in for x, I plug negative x over 3. So I'll have negative 1 to the n over n plus 1 times negative x over 3 to the n plus 1. And technically that's job done, but we could write it more nicely, and we should. So this is going to be the natural log of 3 plus sigma n from 0 to infinity. We'll do this in a few steps. Negative 1 to the n over n plus 1 times, and then here I'll have a negative 1 to the n plus 1 over 3 to the n plus 1 times x to the n plus 1. And some of these terms can play together. Like these two can play together. Negative 1 to the n times negative 1 to the n plus 1 is negative 1 to the 2n plus 1. So I get negative 1 to the 2n plus 1 over n plus 1 times 1 over 3 to the n plus 1 times x to the n plus 1. And then finally, because 2n plus 1 is always odd, you know that negative 1 to the 2n plus 1 is just negative 1. Because when you raise negative 1 to an odd power, you always just get negative 1 out. So this is just a negative 1. And that can come out of the series and make this plus a minus. So I get ln3 minus sigma n from 0 to infinity, 1 over n plus 1, 1 over 3 raised to the n plus first power, times x to the n plus 1. And this would be my final answer. Nifty, right? You can kind of smell where this is going. If you begin with the series for the natural log that I gave you, you can find a series for any other log function just by doing some combination of this sort of stuff. The other problem here will go a lot faster. It was like x squared times the inverse tangent of x cubed. And here I want to recall that the inverse tangent of x has power series sigma n from 0 to infinity, -1 to the n over 2n plus 1 times x to the 2n plus 1. So x squared times the inverse tangent of x cubed is x squared times this series with x replaced by x cubed. Which is x squared times, I'm just going to clean up that power. I'll have -1 to the n over 2n plus 1 still. X cubed, all to the 2n plus 1 power is x raised to the 3 times 2n plus 1, which is 6n plus 3. So my function here, now I can bring the x squared inside. Will be x to the 6n plus 5. All right, when you bring the x squared inside and multiply x squared by x to the 6n plus 3, you add the powers. 6n plus 3 plus 2 is 6n plus 5. So these are the last two examples for today. This is one of the reasons why those important power series are important, because they give us a starting point for finding more complicated series. It's not the only reason they're important. There's actually other reasons as well, but we'll get to those next time. Wednesday, when we meet, I'm going to do two things. I'm going to solve a few problems for you from this current homework set, whatever you guys would like. Homework 11 is going to open right after class here. And then we're going to introduce Taylor's theorem. Taylor's theorem is a big deal. It was the first kind of general result that said if you have a nice function, then you can change it into a power series. Even if it's not geometric, even if it's not the integral or derivative of something geometric, there's a formula. Maggie, this x cubed is being raised to the 2n plus 1 power. So I'm using that rule for exponents. It says like x to the a all to the b is x to the a times b. So I multiply the 3 and the 2n plus 1. Okay, so next time is Taylor's theorem. Taylor's theorem gives you a formula for finding power series of pretty much any function. That's a big deal. And then, lads and ladies, we will be done with all things series related. Just be aware that the Taylor's theorem section is not going to be easy. It's formula dense. There's some formulas that are kind of hard to work with there. but you're almost out of the woods as far as series are concerned. And then we can go focus on some other applications. We can focus on some ways we can use all the things from this semester to solve cool real world problems, geometry problems, all sorts of good shit like that. All right, I gotta let you guys go at this point. I hope you have a lovely rest of your day. If you need to talk to me about anything, exam grades or anything that you're worried about, please don't hesitate to do so. I have an office hour this afternoon from 3:30 to 4:30. And as always, I can be reached by Canvas messages or emails. Okay, take care.